What is Coulomb's law? Coulomb's force, named after the physicist Charles Augustin de Coulomb, describes the fundamental interaction of electrically charged things. It is a fundamental force of nature, similar to gravity, that determines how charged particles attract or repel one another. If two items have the same charge, both positive or negative, they will repel each other. While opposite charges, one positive and one negative, will attract each other.
How does Coulomb's law apply to real-world situation? Coulomb's law, which describes the force between electrical charges, is most accurate when applied to point charges. This is because in real-world scenarios, when two charged bodies interact at a distance, they induce opposite charges on each other. This induced charge can significantly affect the net charges on both bodies, as well as the distance between them, which may cause deviation from the idealized calculation based on Coulomb's law.
Despite these complexities, Coulomb's law has numerous practical applications in our daily lives. In offices, photocopiers use this principle to attract charged toner particles and create document copies. In industries, it is applied in powder coating to ensure an even paint application on metals. Environmental systems also utilize Coulomb's law to remove air pollutants by charging particles for easier removal. We encounter its effect in simpler situations, such as when a rubber balloon sticks to a wall or when camphor attracts paper beads.
Understanding and applying Coulomb's law not only helps in these everyday uses, but also serves as the foundation for further innovations in fields like electronics, nanotechnology, and environmental engineering, where precise control over electrical charges is essential.
What do you expect to happen in this experiment?
The experiment is designed to demonstrate in alignment with Coulomb's law that two objects with the same electric charge will repel each other, while objects with opposite charge will attract each other. The occurs due to the interaction between the charges when like charges are brought close together. They experience a repulsive force that pushes them apart, and when opposite charges are brought together, they experience.
Welcome to our exciting experiments on dancing ball covered by Coulomb's law. In this experiment, we will demonstrate the principles of electric charge and repulsion through a fun and simple setup.
Ready all the materials needed. Gather all the materials required for the experiment.
Ensure that each item is clean and ready to use to avoid interruptions during experiment.
Prepare the styrofoam ball covered by aluminum foil. Cover them completely.
Take each styrofoam ball and wrap it tightly in aluminum foil. Ensure the foil completely covers the ball without any gaps. Smoothing out the foil will help create a uniform surface. This step is crucial as the aluminum foil allows the ball to conduct electricity, which is necessary for them to react to the electric field.
Create the base with an illustration board. You can add a side to secure the styrofoam balls.
Get the illustration board to a size that can accommodate the aluminum foil and the acrylic sheet. To prevent the styrofoam balls from rolling off during the experiment, you can add a low border around the board's edges using cardboard strips, forming a shallow enclosure.
Lay the medium-sized aluminum foil on an illustration board.
Place the medium-sized sheet of aluminum foil flat on top of the illustration board. Make sure the foil is smooth and free from wrinkles. This foil will act as a conductive base to help the electric field necessary for the experiment.
Place the cardboard blocks on each sides of the foil.
Position the cardboard blocks on the both sides of the aluminum foil. The block should be sturdy enough to support the acrylic sheet and keep it elevated. The space created by the blocks will allow an electric field to form between the foil and the acrylic sheet.
Carefully place the acrylic sheet on the top of the aluminum foil, resting on the cardboard block.
Ensuring it rests evenly and securely. The sheet should not touch the aluminum foil directly, as the gap between them is essential for electric field to develop.
Rub the cloth to the acrylic sheet.
Take a cloth and vigorously rub it on the surface of the acrylic sheet. This action generates static electricity through friction, charging the sheet.
Place the styrofoam balls onto the acrylic sheet.
Carefully place the aluminum foil wrapped styrofoam balls on top of the charged acrylic sheet. Spread the balls out evenly across the sheet to avoid clustering, which helps to clearly observe their individual movements.
Observe the results. Watch as the styrofoam balls begin to move or dance on the acrylic sheet. Due to the charged acrylic sheet, the balls, having acquired the same charge, repel each other and the sheet itself. This repulsion demonstrates Coulomb's law, where charges repel, resulting in a distinctive movement of the balls.
How did you charge the objects? By rubbing the cloth into the acrylic sheet. Initially, the charges on the acrylic and balls are neutral, but as we rub the cloth to the surface, it creates a negative charge on the plastic, and so the balls adjust their position, with the negative charges moving away from the plastic, while the positive charges are attracted.
Important to understand Coulomb's law.
It is important to understand Coulomb's law because it is a fundamental principle of electrostatic forces between charged objects like protons and electrons. This law states that the electrostatic force between these objects depends on two things: the amount of charge on each object, called electric charge, and the distance between them.
Coulomb's law also helps us to understand other electrostatic phenomena such as electric fields and potential differences. An electric field is a region of space where there is an electrostatic force that can cause other charges to experience a force. Potential difference is the amount of electrical energy per unit charge between 2 points in an electric field.